Welcome, everybody. Thank you so much for joining the webinar and providing so many comments and questions about modeling. There is tremendous diversity among you, including a wide range of modeling experience, ranging from complete beginners to very experienced modelers. So before we bring in our four speakers, I'm going to start with an overview of modeling to talk about why we use models, how we make decisions about selecting models and developing them, as well as big considerations and limitations that we always need to keep in mind. And I want to emphasize that the webinar today is not about teaching mechanics. It's about helping to think strategically about the modeling process. And I'm really excited about our four speakers. They're all very experienced modelers, and all of them bring distinctive perspectives about models and what they do and how they can help address questions. But before we get into the webinar, let me introduce who is here today. We have, like I said, a very diverse group. We have almost 225 registrants so far. And it's amazing how equally divided you all are among different sectors, public, private, academics, NGOs. And one thing that's just exciting and amazing is where you come from globally. We have 5 continents represented, almost 30 different countries. So you can see who's here right now. And this, to me, just shows how global and interdisciplinary the interest in fire modeling really is. And this diversity is also reflected in the questions that you submitted. So I read through all of your questions and I see that they fell into some broad yet divergent themes that I've tried to put here and lay out. Some of them had to do with the modeling process, such as how do you couple models together, accuracy issues, performance. But other ones were focused on how do you incorporate human factors into the modeling process, management, policy choices. Some of the questions were about how do you address specific issues like modeling peatlands or deforestation, integrating remote sensing. But then there are also questions that have to do with model usability, such as access, governance, transparency. What skills do we need to be able to use fire models? How do we build a career in fire modeling? So this breadth is actually a diagnostic to me. It tells us that the gaps in modeling aren't just computational, they're not just scientific, but they're also structural and they're also institutional. And it also reinforces what I suspected is that we don't just need better models, we need better ways to match models to the objectives, because there are many objectives. And because there were so many questions, we can't answer each individual one here today, but I'd like to remind you that the Global Wildfire Collective has a discussion forum, and I'll provide a link to that at the end of the presentations today. But I would love if we could start a conversation about modeling over in that discussion forum. So moving on, I want to sort of set the stage by zooming out and thinking about wildfire in general, that it is a complicated thing. So we all know that for combustion or a flame to occur, 3 things need to come together. And this is your classic fire triangle, right? It's heat, oxygen, and fuel. But imagine that someday a fire starts on the landscape. What happens when that fire starts and the behavior that the fire illustrates is a function of many more things? And now we can think of this as a fire behavior triangle. How it behaves depends on conditions of the vegetation, the type of the vegetation, the volume of the vegetation, climate conditions before and during the day of the fire. And whether or not that fire reaches that house depends on other factors like topography, suppression resources, how close is the fire to the house. So at this scale, an example fire modeling question might be, from an operations specialist wanting to predict how long will it take for this fire to get to that house. So, So after a year, vegetation starts to recover, and how it recovers is going to depend on a whole new suite of factors, like yearly climate, what were the vegetation conditions like beforehand? What are the traits of the species? Has somebody planted new vegetation? A fire might start in this time scale. So at this scale, an ecologist might use a model to say and to ask, why are species recovering and which ones? Finally, after a couple of decades and at broader landscape scales, the system starts to change again. And now it's dependent on a whole range of other factors. Now our fire triangle moves into a fire regime triangle. And we might see repeated fires. We might see vegetation change that are a function of both climate and vegetation feedbacks over time. Species may invade. New housing developments may come. More people are starting ignitions. So at this scale, again, many things are happening. And an example question might be from fire managers who want to know, well, where do we put fuel breaks on this landscape to protect the housing development? How might vegetation change if fires keep repeating in the same area? Where's housing loss most likely to occur? And then finally, at even larger, at the broadest space and time scales, we're moving in terms of global fire patterns. And these are where fires are affected by large climate atmospheric patterns. There's carbon and water cycling. There are issues such as deforestation, continental biodiversity, long-term public health impacts. And these are shaped by big factors like governments or policy cycles. So at this scale, academics might, for example, use a model to understand the social drivers of deforestation or the factors that are affecting carbon budgets across the earth or how smoke is crossing borders. So in summary, I show you these to really remind us that fire is a complicated thing because it is a coupled human natural system that plays out across all space and time scales. And at every one of those scales, there are multiple different factors and drivers and interactions that are affecting the the occurrence and behavior of fire and the outcomes that those fires have on people and ecosystems. And they all change depending on where you are geographically. And so, of course, the number of questions that we may have about wildfire is almost infinite. And again, they span multiple disciplines. So all the way from physical and atmospheric science, asking how does turbulence affect ember transport, to economics, how do insurance companies price policies fairly, urban planning, how are community layouts affecting the exposure of wildfire? So how do we answer these questions? The webinar today is really about understanding the process of this. Traditionally, you can rely on fieldwork, looking at how species are responding and recovering after a fire. You can set controlled burns and observe what's happening to the behavior. You can do case studies of fire damage to a house. But the problem with these traditional methods is that wildfire operates across all of these scales that we discussed, and it's also random, and it's physically difficult to actually go out and manipulate nature or to test hypothetical scenarios sufficiently enough to answer the questions that we have. So this is where modeling becomes essential. Traditional methods can show us what happened, but modeling enables us to explore what could happen. Yep, switch. Okay, so what's a model? Generally, it's a simplified representation of reality that allows us to explain, explore, predict system behavior, and support decision-making. So naturally, following that, what is a fire model? It is a representation of the physical, biological, and social processes that describe or predict wildfire behavior, effects, or risk. And I don't want to steal this from Michelle, so I'm not, or Melissa. Wildfire is complicated. And like fires, fire modeling spans space and time scales. So we have models that can simulate the physics of an individual flame that happens on the scale of, meters and hours, all the way to fire spread models that can look at what we showed with fire spreading across the landscape, to forest landscape models, and again, moving up to models that can simulate Earth system processes across the entire globe. All of these different scales of models require different assumptions. They require different equations. They have different data that they use, and they have different computational costs. Today, just FYI, the speakers are going to cover the range of scales vaguely where you see in this blue circle. So then which one do I choose? While models are meant to simplify, fire is so complicated that there are literally thousands of models and model combinations. I decided to do a review of the literature and look at some modeling review papers because I was curious how many fire models are actually out there. And in my estimate, I came up with about 15 or 20 distinctive families of fire models. This is not including what they're coupled with, such as urban growth, economic, or climate models. And from that, there are up to 4,000 unique individual fire models out there, ranging from fire danger indices to fire risk, quasi-physical, smoke dispersion models. And the thing is that with emerging AI technology, the rapid development of more sophisticated data, the number of models is growing. And so the complexity is good because it shows that our field is advancing rapidly. There are many options, but the abundance of these models also increases the risk that you might have a mismatch between objective and your question. And this is why we're here today. So are you feeling overwhelmed yet? I am. But actually, it doesn't have to be that overwhelming. If you think about it as a decision framework, how do you select a model? Well, the most important thing is to not start with the model, but start with your question. What is the purpose? What are you trying to do? What's your objective? Is it tactical for fire operations? Is it management questions? Are you trying to understand something theoretically? And once you have that narrowed down, which we call fit for purpose, by the way, then you can start making more decisions about, well, where, what is my time and space scale? Days, decades, meters, continents? What are the processes that I need to include in this model to be able to address the questions I have? What outputs do I need? Do I need a response time? Do I need a ranking of priority decisions that are going to be most effective for my objective? Or maybe I need maps to help determine where somebody might need to go. And then finally, a really important question and consideration is what are the resources you have available? Do you have access to the appropriate data? Are the data of sufficient quality to answer your question? Do you have the technical infrastructure and computational resources to be able to run some of these models? And do you have the expertise to understand how to use these models correctly? Something that I like to think about is that sometimes it's more important to know what can be done than to actually know how to do it. Because this is where collaborations come in. This is where you can find technical experts to help you. But understanding the design of your modeling process is most important. And it is a process. Modeling, whether it's a simple or a complex model, is not a software program, is not pushing a button. It follows a sequence of decisions and checks. So again, it starts at the beginning. What are your questions? What's the scale you're looking at? What are the assumptions we need to make to simplify reality? And then the next step is to assemble your data, calculate parameters, figure out what your inputs are, define the structure of the model. And then you run the model and you figure out which are equations that we need, what are the algorithms, what are the rule sets that we put into it. But you're only part of the way once you're running the model. The next part is really important, and it's a part that a lot of people aren't aware of or they skip it. But you have to also involve steps of evaluating the model as you go through the process. So sensitivity analysis is looking at the influence of the parameters. How do the results respond to the different parameters? What is the uncertainty in your model projections as a function of these input parameters? Does it come from the assumptions you have? Is it the data? Can you quantify that uncertainty? Verification is something that refers to looking at the performance of the model relative to the way you've implemented. Is my code correct, and is the model actually doing what I told it to do? And then finally, validation is running your model and evaluating it against independent data. Is your model actually simulating or, representing the reality fit for the purpose of the model? So then we go to predictions, projections, scenarios, whatever the ultimate output is. And this is what is used for whatever your purpose is. Ultimately, I think the final step, and it's one that we haven't really gotten to yet, is how do you measure the outcomes of fire modeling? You've got the outputs, and people use model outputs to make decisions. But are those model outputs that are resulting in decisions actually changing outcomes on the landscape? And if they are they desired outcomes? So I propose that we need to start looking at that. There are limitations. George Box famously said, essentially all models are wrong, but some are useful. And he followed that by saying, well, since all models are wrong, the scientist must be alert to what is importantly wrong. These are just a couple modeling principles or philosophies. There are more to come, but they're ones that I thought of, which is things that we need to remember for responsible fire modeling or modeling in general, is that all models require assumptions, and those assumptions affect the outcomes of your models. So understanding what has had to be simplified to run your model, and then how do we interpret the results according to those simplifications? Are the ignitions expected to remain in the same place over time? How does that affect the results? In these areas, do you hold weather constant within a large area? How does that affect your output? Also, uncertainty in modeling is not a weakness. It is inevitable. Every single model has uncertainty because you're simplifying reality, right? And one of the trade-offs of modeling is that the more complex you get, the more aspects of reality you start bringing into a model, the more you start coupling models with other different kinds of models, the more uncertainty starts to propagate through the process. And there are many ways to go about identifying, well, where are the sources of the most uncertainty? How do I quantify them? But then importantly, how do I communicate them? Transparency in modeling, one could think of that as being responsible in your modeling. There are a lot of black box models out there, and they're fine, but they do hinder interpretation because you can't understand the outputs if you don't understand how the model got to those outputs. And so where possible, it's important to disclose, to describe, and to visualize what the limitations and what the sources of uncertainty are in your models. And then finally, to add on to that, some lessons to remember before we get into our speakers. Another quote that I love from the mathematician John Tukey is, an approximate answer to the right question is worth a great deal more than a precise answer to the wrong question. So again, I can't say it enough, fit for purpose. Start with your objective, then pick your model. Inputs drive outputs. We've heard of garbage in, garbage out. Think about what your data are. What are the quality of your data? Can they really help you address your question? Are they the right scale? Domain of validity is addressing the fact that processes are not stationary over space and time. Relationships between variables may occur in a certain place in a region, but they may not occur continually over time, and they may not occur in a different landscape. So it's important to consider that when you develop a model, it applies to the places and the times and the conditions where you trained that model. Maps can mislead. Maps are very seductive. A pretty map is really easy to fall into and believe, and it's important to explain, label the assumptions, put something on your map, explain what the limitations are, because maps can hide a lot of uncertainty and they can vary widely depending on what kind of modeling approach you're using. There's always limitations. It's not a weakness. Interpret in light of them. And finally, people matter. We need to start incorporating social science and human behavior into our modeling process and continually remind ourselves that the world is changing rapidly, and this is something we also need to acknowledge. So with that, I am very happy to begin our presentations with our four experts. We're going to have all four presentations first, and then we will hold the discussion and the questions for afterwards. So if you have questions, write them down, put them, Robin, put them in the question and answer box?
Yes, in the Q&A.
Q&A. So briefly, our presenters today, we've got Dr. Michael Goner, presenting wildland modeling at the landscape scale, and he'll be looking at applications at the wildland urban interface. Dr. Rob Scheller is one part of forecasting future fires with forest landscape models in the Southern Appalachians. Melissa Lukash is following up with that, looking at boreal forests in Alaska and Canada. And then finally, Trent is going to be talking about fire risk modeling, a range of approaches in Australia. And we will start with Michael. So Michael, I will have you tell me when to change.
Sounds good.
Okay.
All right, so I'm happy to excuse me, happy to be speaking here today. Let's change to the next slide. So I only get 10 minutes and go ahead and play this. So I'm going to talk a little bit about landscape scale fire modeling. My work ranges from experiments into theory and modeling. And the modeling that we tend to do is actually where we do larger scale modeling and we use what we do experimentally and try to put that in. We could jump halfway through the video. So this is just, well,
Uh-oh.
anyways,
Oh, no.
it's all right. It's different when you're not controlling it. So
Oh,
this is
wait,
a
hold on.
prescribed burn, and the reason I'm showing this is there's really a lot of complicated subscale physics that happens. And so the models we use at landscape scale are simplifying so many factors from the fuel type, from the way that embers are falling, the way that the heat is coming. And so there's a lot of subscale things that are happening that we are just missing, and we have to find appropriate methods to model quickly. So next slide. So when we look at the wildland fire models that we do, we are really restricted by the scale. So if you click next, you'll see to start off, the actual combustion physics that's happening of the flame, the fire line, the combustion's happening at millimeter and smaller scales. There are molecules reacting, but we often ignore that small scale chemistry and focus on things like flame lengths and the width of the fire line. And these dynamics are controlling the spread of the flame. But this is happening in a broader landscape scale. So click next. And you can see that the weather, of course, is going to be modifying the flame. But this also very much depends on scale. The velocity of the wind at the base is going to be different at the flame height and is going to be different up at the treetops. This is also going to change dynamically across the landscape. Next slide, next click. And that's what I mentioned here with the canopy and the fuel. Fuels, we simplify their classification because, you know, the way they're actually finally put together and the way they're grouped is going to change the way they burn. A single piece of paper, a piece of wood versus something that's shredded and fluffy will burn completely differently. And next slide. Homes in the wildland urban interface get even further in complication, right? We're thinking about vegetation, which is somewhat homogeneous. Maybe not perfectly. We think about trees here, grass here. A home now is a single object, which is going to ignite. It's going to burn a longer time and complicates. Next slide. If we were actually interested in the emissions from the fire, this even gets larger because now we have to look at broader scale weather that's going to transport. And even though the mixing happens at small scale, the plume and the smoke is going to happen at a much larger scale. Next slide. So wildland fire modeling relies often on these landscape scale models. In the US, we use like Farsight Flame Map. And Alexandra mentioned many other models that are out there. Often here, they're 30-meter grid resolution, so it's not super fine, but it's enough to classify wildland fuels. And as you can see on the right, you see we take things like the elevation slope aspect of fuel model, put that together with canopy properties, and then we can actually run the model and submodels to look at an elliptical model of spread. Now, that's sort of the traditional way the Forest Service does most of their modeling. It doesn't couple to atmospherics, and there are many other approaches to this. I'll talk a little bit about another Eulerian level set model, Wildfire, that we use, but they're all based on very simple kind of fire spread and rely so much on the input, fuel, and weather. And the goal here, of course, is to model the fire progression over time. Now, there are also coupled approaches, and the coupled approaches, which we'll not talk about today, are where the fire and the atmosphere and the wind interact together. Fire, as you saw earlier, fire behavior is driven by topography, fuel, and the weather and the wind or the humidity. Now, that atmospheric wind that's being applied is changing dynamically. It doesn't matter as much when it's sort of not being influenced as much by the fire. When you get larger fires or large fuel loads, it starts to play an important role, or when you have complex geometries like on the right. So there are other models such as that couple with WRF or FireTech, FDS, WFDS. We won't talk about these as much today. Next slide. So what I want to talk about is where we take traditional wildfire modeling and we try to move that into the context of using it to solve this very pertinent problem of wildland urban interface fires. So when wildland fires move from vegetation into communities, they can cause massive destruction. And what you see here, the Tubbs Fire in California is a great example. This is a suburban neighborhood, which when one looks would not immediately think that this is a huge wildfire risk, but the fire literally jumped over highways, spread into the community, and became a conflagration spreading from structure to structure. So what you can see is that these losses have been dramatically increasing. We see this a lot in LA. And we need a solution to take what we're existing doing in wildland fire, which is devoted more towards modeling fires that are, operational. So where will the fire go? Where do we do suppression or risk analysis? And adding to that spread through structures. Next slide. So this is our challenge because these fires are dynamic and they stop in certain places, like right here. Why did it not cross over the road? Was there a firefighter there? Or was it the weather changed? Or is there something interesting about that spacing? Next slide. So to model this, we have to consider three pathways. In wildland spread, we have usually in the US the Rothermel model, which is simplified and kind of ignores some of the physics. For these wildland urban interface, we have to specifically account for radiation from the fire to the structure or between structures, direct flame contact, which is these small scale flames moving through fences, mulch, and small features up to the house, or embers and firebrands, which if you click the next, click twice, whoop, I skipped it, but embers or firebrands,
no.
which are going to be the small particles moving through.
Oh, sorry. I'm trying to
go to the next slide. We're good.
Okay, sorry, Michael.
So let me show you how this is all put together. When we do exposure from fire modeling, we take the vegetation weather topography, which is typically pre-run, and then we use this in our model, whether it's Farsight or Elm Fire or whichever, for the surface fire, the crown fire, which spreads through the canopy, and ember models. We're using the Elm Fire model, but they all rely on this sort of same concept. However, every model usually uses similar inputs, but puts them together in slightly different ways with slightly different variations. And the output of that is going to be the spread rate. So where is the fire gone as a function of time? You can also sometimes extract the ember cast. The ember cast is great because that tells you a little bit about where that's projecting. And the flame length. The flame length tells you about the fire intensity. How big was that fire that occurred? The next slide. There are, of course, those limitations I mentioned. And I think I want to demonstrate this with basically a rerun of the Camp Fire, which occurred in 2018 in California. You can see there marked the town of Paradise, where over 18,000 structures were destroyed. In the current fuel maps, there's basically no spread at all there because structures are marked as non-burnable. So this is the challenge that we have to tackle. Next slide.
Oh, that
Wow.
was
Okay, wow. All right. So our new framework is to take the wildland modeling framework and add to that the direct flame contact, radiation, and spotting, and to treat structures as individual elements based on this. And so this spreads the fire through structures and can include things like mitigation, because we can actually look at properties for the ignitability of the building, the probability of ember ignition, that changes from structure to structure. And it links structures to wildland, which is spread-based to ignition-based, and links the spread rate and time together. And the key outputs that are interesting is we can not only look at how it spread, but also what the heat fluxes were, where the embers were, and what modes caused ignition in different areas. Next slide. Let's keep going. So you can see a reconstruction now on the right, and sorry they're not plotted in the same scales, but the structures destroyed are now marked on this new map. And you can actually see this is basically based on time of arrival, how we modeled fire spread then through the town of Paradise, and you can see how it much better fills the actual area. There was a little bit of northward progression. Every model has uncertainty. Data inputs have uncertainty. Doesn't include fire suppression, doesn't include other things on the ground that weren't known and are now burned over. But it allows us to really model through the urban area that was missed in the original component. This, of course, would be a major issue if we are looking at trying to understand a fire spread that could have impacted a community and we would have seen no spread, but actually it can go right through that community and propagate on to more wildland. Next slide. So as an example, this is showing for the Thomas fire that occurred in California. It's again another wildfire. It was a little more south from Northern California, so more scrub fuels. You can see that the model's done fairly good accuracy of reproducing the fire. Nothing, of course, is perfect, but we can see the fire progression with time. It successfully captures spots and ember cast. Now, one important thing is that no run is a single run. Um, we typically use ensemble-based models, while Farsight does a single run. We often focus on ensemble models because there's incredible uncertainty in the inputs, whether that be the weather and the ignition, et cetera. And so we want to run multiple instances and look at averages or look at specific cases. And so here you can see how that run kind of came together. And given the limited inputs we have on these fires, it gives reproduction with fairly good accuracy. Next slide. And importantly, it now gets to those urban areas. And we can see things like heat outputs, so we can understand some of the heat fluxes between buildings. This, of course, is not perfect in any way, shape, or sort, but it gives us an estimated range of which processes were dominating and where structures were actually moving towards ignition and not. And now that we've recently completed campaigns of structure burns at IDHS here in the US, so actually burning structures in a large-scale wind tunnel, we now have some data to start matching this and improve the models. Next slide. The big application of this, which in 10 minutes I have no time to discuss, is where we don't just reconstruct fires, but we move into wildfire risk assessments. And that's where most of our efforts are focused. There is a big framework, at least in the US, for landscape scale wildfire risk assessments. However, this doesn't translate down to the wildland urban interface. So there's a great program that looks at risk to individual communities, but it treats the whole community as a whole. We're most interested, where in the community is the biggest risk? What is the impact of particular mitigations that you will do? And how do you make those changes in the landscape or mitigations within the community, like hardening or defensible space, and combine those to get the biggest, bang for your buck in terms of risk mitigation? So that's, essentially where we're going, but it requires us to focus not just on an individual property, but to look at the possible spread through communities in many different ways and to kind of bridge those scales from the large scale wildfire and its occurrence down to the individual structures and communities. And this is hard because, again, the models operate different scales and different timelines. And so that's a big part of our work is trying to put that together using the coupling of the existing wildland fire model with wildland urban interface. Next slide. So in conclusion, sorry, we have a very short time to review that we've developed a new model which works at spreading the fires into the urban area. There are other approaches that exist in literature. There's some other urban models which are independent. There's some where you can make approximations of exposure. But for certain applications, I think it's really important to actually model the spread into and within the urban area. And so we've done that and coupled that to an existing wildland model. And the predictions are fairly good. When we talk about 70, 80% accuracy on burned area and structure, that's well above norm. Actually, the potential accuracy can really range in these models because the input data sets and there's so many uncertainties. But like I mentioned, there's a lot of uncertainties. We don't know a lot of the structure information. We know fuel information in the wildland, but we don't have it down to structures, and fine scale details matter. We need better resolution, and we still have to figure out how to put that together for risk assessments and which weather do we use to model that. There's a lot of unknowns that we keep working on and keep applying. So I'll leave it at that and look forward to questions after the rest of the presentations.
Awesome. Thank you, Michael. That was great. We now have Dr. Robert Scheller. He's the Associate Dean for Research at North Carolina State University, talking about social dynamics and climate change in the Southern Appalachians, as I told you. And so Rob is going to share his screen. I have to stop sharing. Sorry.
Yeah.
Okay.
Great. Hopefully you all see my screen. Yes. And you can hear me. Good. Thanks, everybody. I am going to work at a different end of the scale than Michael was. We're going to talk about forecasting fire regimes. And I'll just note that my talk is a little bit of a setup for our next speaker, Dr. Melissa Lukash. So I'm going to introduce a lot of concepts and give a very brief case study, and she's going to run with it from there. Okay, so what we use, and there's a large group of us working across North America and the rest of the world, we use forest landscape models. And forest landscape models are designed to capture the drivers of change and uncertainty on forested landscapes. And so we're looking at disturbances. Of course, we're talking about wildfire today, but also insect outbreaks, hurricanes, et cetera. Incorporating human actions on the landscape, including harvesting, prescribed fire, tree planting, land use change, et cetera, and also featuring the effects of climate change. And so forest landscape models, as Michael pointed out, allow us to explore possible futures given diverse external drivers. So developing what-if scenarios about the future, and I'll give some examples of that. And so examples of the kind of questions that forest landscape models allow us to ask and hopefully answer, such things as, can management mitigate the effects of climate change? How can we avoid catastrophic wildfire? What management strategy will be optimal in future decades? And so the model we specifically use is called LANDIS2. Again, this is a forest landscape model. It's been designed and tested for over 30 years now. And as expected, it's optimized for understanding forest landscape change. So the typical extent is anywhere from 100,000 to 10 million hectares, sometimes a little smaller, sometimes a little bigger. Typical duration that we're looking at is 50 to 100 years into the future. And our model assumptions reflect these expected scales. And so in the map here are just two landscapes, just as an example. I guess this mostly works if you're from North America. And what we see is a portion of northern Minnesota and all of northern lower Michigan. So these are Minnesota was about 200,000 hectares, and the Michigan landscape is about 350,000 hectares in size. So that's the typical scales that we're looking at. And so LANDIS2, this is kind of the big overview. And so we have the landscape on the left, that's Lake Tahoe Basin, which straddles California and Nevada in the western United States. We take that landscape, we divide it into a grid of interacting cells. And within each cell, we have, so in each individual cell, we're simulating succession happening, so vegetation growth and change over time. And then what really unites this landscape is a spatial interaction of these different landscape processes over time. So think about seed dispersal, we have wildfires, harvesting or thinning, insects, all these different processes are stitched together over space and time within the model. Climate change is affecting many or most of these processes over time. So of course, climate change is affecting succession, growth, decomposition, it's affecting wildfire, it's affecting insect outbreaks, and it affects humans and human behavior over time. Humans are not passive recipients of climate change on landscapes. Rather, humans are adjusting how they behave over time as well. Okay, and so here's a typical approach to using these kind of models. You start with a lot of data science, right? We want to create a digital twin of the landscape as it exists today. So we create our digital twin. And then we also work with stakeholders to develop scenarios. The scenarios are specifically designed, as Alex said, to meet specific objectives. Like, what are the questions our stakeholders want us to attempt to answer? What is important on their landscape? What keeps them awake at night? We put together the data science and the scenarios. We run it through the big landscape change model. And then we produce these change projections, again, decades into the future, generally large landscape areas, produces a lot of maps as well as, time series of important metrics of landscape change. Okay, specifically today, I'm going to talk about how do we simulate wildfires within the landscape, within the Landis framework. And so we use what's called the social climate fire extension. And this is a fairly unique extension. I'm just going to walk through the principles first. Of course, as mentioned by Alex, we need to capture the influence of climate and fuels and fuel treatments and topography. We also want to capture the spatial and temporal patterns of fire suppression. So I forgot to say, one of the guiding principles of this whole thing is that fires are not simply a biophysical phenomenon, that the social components are as important as the biophysical. And fire suppression is an important social process that happens on landscapes. We want to capture the spatial temporal patterns of wildfires, prescribed fires, and accidental fires. These three different types of fire regimes have really different controls, different ignition patterns, different suppression patterns, and different types of management used to address these three different fire types. And again, I said this before, we're trying to project fire regimes for 50 plus years. And we'll see there is some fire behavior underneath this, but we're primarily interested in how fire regimes will change in future decades, not as much the individual fire, how individual fires will behave, as Michael described. Not that that isn't important under certain contexts and to address certain objectives. And so because of this, we really emphasize top-down versus bottom-up processes. So rather than looking at, a lot of road thermal models start with fuels and you build from fuels, you scale up from there. We really began by looking at what are the overall patterns of fire on these landscapes over the last 20 to 30 years. And we use that to build our model, again, looking from the top down rather than from the fuels up, so to speak. And so we're starting with, as I just said, landscape scale controls on fire regimes. And then we're scaling down to individual events and cell scale mortality of vegetation. And so therefore, we're really trying to maximize the use of remotely sensed data and landscape scale data products to drive our prediction, our wildfire forecasting engine. Now, I said that there is some fire behavior underneath this, and I feel obligated to describe this to some degree. Of course, every fire starts with an ignition, and it spreads. Spread is contingent upon fire suppression. And then from there, we're estimating DMBR. So really broad scale, landscape scale estimates of DMBR are used to determine what was the intensity of the fire for each cell. Based on that intensity, then we describe what was the mortality of individual, of the vegetation on each cell. Okay, and here's my very brief case study. So here's a landscape we've been working on lately. This is the Southern Appalachians, which straddles several states in the eastern United States. It's a very mountainous, rugged area. I really should have included pictures for this talk, but I forgot to. It's rugged, but this mountain range is about 500 million years old, so it's entirely forested. It's not, how do I describe the Appalachians? Very tall hills, forested hills, very steep, tall, forested hills. Think of like the Terai region of Nepal, for example. So we've done we've had research ongoing here for the last 6 or 7 years, focused on a variety of things: wildfire, climate change, and management, that I'll talk about in a moment, but also alternative silvicultural systems to ensure oak regeneration. We've done research on prescribed fire and smoke production, as well as climate change and bird habitat change over time. And so again, this starts with a lot of data science. We have to create that digital twin of this landscape. So we're pulling together, vegetation data, soils data, climate projections. What do we know about carbon and nitrogen on this landscape today? What are the current business as usual management strategies happening across this entire landscape? I should have said this landscape is about 500,000 hectares. And then we have to look, what are the historic fire records that will inform our future fire forecast? And so specifically, I'm going to talk about one paper. This is led by my former PhD student, Zachary Robbins, who's now at Los Alamos National Lab. And the big question was, well, how will drought change this landscape? Particularly, how will drought change fire regimes on this landscape? So we focus on drought trends rather than identifying particular, climatic models or particular RCP futures. We really try to pick out distinct drought trends from all the different climate futures that have been produced for the Eastern United States. So about 20 different climate futures that have been produced. We focus on 4 that highlighted 4 distinct drought futures for this area. Number 1 was a low drought trend, so some moderate increase in drought over time, but pretty low variance from year to year. So year-to-year variance was on the low end. The second one was low drought trend with high variance from year to year. So even though the drought trend was modest, there was a lot of year-to-year variability. The other extreme was a high drought trend with low variance and a high drought trend with high variance. So those are the 4 scenarios we wanted to test for this landscape, and looking particularly at how did fire regimes change into the future. So here's some maps demonstrating that. So up on the upper left-hand side, you see low drought trend, low drought variance. And this is not a lot different from what we've seen historically. What you see is the different colors indicate the fire rotation period, with the dark red being, high fire rotation period, so frequent fire, and the black areas are, greater than 200-year fire rotation period. That's the low drought trend, low drought variance, very similar to historic patterns. We see that increasing with low drought trend, high drought variance. And in the lower right-hand corner is high drought trend, high drought variance. We're seeing fire all over the landscape into the future under that particular climate future. And if we look at those trends over time, it's clear that a huge distinction between all the other ones and high drought trend, high variance. And, there's of course, a lot of assumptions about, what are the future trends of drought. The high variance seems to be bearing out. If we've done an analysis recently about drought trends across the Southeast, and drought variance has been increasing substantially over the last 25 years. We could debate whether it'll be a high trend or a low trend. And there's just a lot of uncertainty in the climate projections for this area. And so we see total hectares burned, just a huge jump if we have high drought trend, high variance. And then if you look out over time, we see it's not these linear increases by any means. There's often kind of a mid-century bump. But yeah, some interesting patterns if you look at change over time. And I'll stop there. Thank you. To you, Melissa.
Can you see my slides? Thanks everybody for hanging in there. Well, wait, let me adjust this a second. No, I can't. Rob gave a great introduction to Landis modeling, and he talked specifically about forecasting changes in vegetation and fire regime. But what I often bring to the Landis community is really this geographic perspective and geographic lens with landscape modeling. So, you know, we know that fire is, oh, sorry, hold on. I just lost my slides. 1 second. There we go. We know that fire is inherently spatial, right? And therefore, the fact that Landis, too, is spatially explicit is really critical for simulating fire regimes. And so in most extensions of Landis, vegetation is represented as this map derived from field data where the landscape represents actual current conditions on the landscape. And in my mind, this really allows those current patterns of vegetation to influence fire processes, as well as capture those feedbacks between vegetation and fire. And unlike some other models, vegetation is not just represented as forest types, like in my map here, but also as species and ages. We know, right, not all pines are created equal in terms of fire tolerance and mortality. You know, we know loblolly pine is much more moderate, like a more moderately fire tolerant than slash pine, which is really fire tolerant with their thick bark. And modeling fire regimes in Landis 2 also builds upon the spatially explicit nature of climate and soil conditions, like soil moisture and soil temperature. As part of a previous grant in Alaska, I built a succession model that we call Dig Succession with a large group of collaborators, including Rob, where we coupled together 4 different models within the Landis framework. 2 are depicted here, GIPL, which is a permafrost model, and Shaw hydrology model. And this succession module simulates multiple layers. You can see the little dots there depicted in the cross section. And this was allowing us to capture the effects of wildfire on soil temperature, and then also to simulate how wildfire affects permafrost as well as hydrology. And you can see with those arrows depicting that soil moisture affects soil temperature and vice versa, and all embedded within this Landis framework. So we can look at questions about how fire regimes and vegetation changes over the long term, like Rob described. And fire, of course, is inherently spatially interactive, right? Fire spread from one area to another, but not all models are spatially interactive. But Landis was specifically constructed to allow cells to interact with one another, like Rob described, allowing fire to spread or halt depending on fuel type, aspect, slope, climate, and other factors like forest management. So most of my work in modeling wildfire has been focused on Alaska, in part because the recent burning of boreal forests has exceeded the fire regime limits of the past 10,000 years. Research has shown that recent changes in the fire regime have altered successional trajectories and could permanently alter forest composition, as well as climate change altering permafrost, frozen soil, and boreal forests, and accelerating carbon release. And my work in Alaska has been as part of several different projects. The first one was this one here that we affectionately called Reburns Alaska. And now I'm part of the Bonanza Creek LTUR. We have a modeling group and now the Wildfire group. So I'll talk about some work that's been done as part of Bonanza Creek. And then I just have a new NSF grant that started this summer. Just started, so we don't have a fancy title or logo. But our project is composed of 3 PIs and a PhD student with a total of 11 cats. So maybe this will be our new logo. I'm not sure yet. But this new project will really focus on wildfire and how it affects conifer reproduction in Alaska and Canada, and specifically looking at those successional trajectories that I'll talk more about. So our ongoing work with Bonanza Creek LTR, this is a manuscript in preparation led by Shelby Weiss, focuses on projecting future changes in the wildfire regime in boreal Alaska, which is outlined in that upper left-hand study area. And as part of this work, we often look at, traditional metrics of the fire regime, like annual burn. And what we often look at is area burned on the y-axis as a function of time, so projecting into the future to end of century, and then looking at these different climate scenarios, with the gray being historical, assuming there's no more climate change in the future, as well as a moderate warming scenario in yellow, and then a more extreme warming depicted in the bottom row with GFDL. And what we're finding is, not surprisingly, that we're having more and more of these large fire years, areas with large area burned. But then with Landis 2, we're also able to look at how the fire regime changes in terms of the seasonality. And our work has shown that under these climate warming scenarios, that we're having greater area burned than historical climate, particularly in June and in May. So in those spring months, larger area burn projected into the future. We've also been looking at fire frequency and how that might change in the future. These are the boreal forests of Alaska, where they burn about every 100, 120 years. But more and more with increased warming and shifts in this fire regime, they're having many areas that are burning with only 15 years between fires, which we of course refer to these short interval reburns. And so these boreal forests of Alaska that are characterized by these coniferous forests, and this picture here is black spruce, and that if your fire interval is 100 years, you're going to eventually return back to your conifer forest. But in many of these areas in the field, we're finding that if there's only 15 years between fire, that we're actually transitioning to hardwoods. This one is a 2-time burn, so you can see lots of snags there. But if this burns again, where you get another short interval burn, you'd actually eliminate those snags and have a lot more bare rock and lichen and hardwoods and very few conifers. So our work has looked at how that annual reburn rate might change into the future. And as you can see with the gray line, right, the reburn rate, which is just those overlapping fires with short intervals between them, it just naturally increases over time because as more time proceeds, you have more and more overlapping fires. But what you can see with the red line is that that annual reburn rate really tends to increase at a much more rapid rate under the more extreme warming scenario in Alaska. We also try to characterize those spatial patterns, again, this geographic perspective, right? Really noting that the areas where you have these reburns differ spatially depending on these different climate change scenarios where you have those, different areas with 2 fires. The yellow areas differ quite a bit depending on the climate change scenario. We've also, with Landis, we've also done a bunch of work trying to look at vegetation transitions. Maybe these alluvial plots where on the y-axis you have proportion of cells on a landscape and then projected into the future, end of century again. And in this case here, the conifer are the dark green forests, so those black spruce forests. And you read them as if, the majority of the landscape here, maybe 60% is conifer forest now, and at end of century, under this moderate warming, it's still fairly, most of the landscape is still conifer dominated, and even under a more extreme scenario, it remains so, just under 1 fire. But what we're finding more and more with these areas with 3-time burns, for example, that although you start at the same place with about 60% of the landscape is conifer, By end of century, it's more like 20% under a moderate warming and maybe more like 10% by end of century, and a huge increase in these broadleaf forests in Alaska. And you can see it again, my spatial perspective is that this is the way the landscape looks now, lots of purple, primarily conifer dominated, but finding that even under a moderate scenario, lots more magenta, a lot more broadleaf forests projected in the future. One of the unique components that we've done as part of our work in Alaska is really also trying to also look at permafrost stability. So underneath these conifers, we of course have these permafrost soils. These soils have been frozen for at least 2 years. And looking at how with increased warming and changes in the fire regime affects the depths of permafrost, and really finding that the blue line is historical, so assuming no more climate change, there'll be just a slight increase in the depth to permafrost, which we know the permafrost is thawing already. So end of century, some declines, but under those climate change, more extreme climate change scenarios, really finding a really large increase in depth to permafrost. And I'll just leave you, Alex tried to steal my thunder, but I'll leave you with my favorite modeling quote, which is to make everything as simple as possible, but not simpler. Thank you.
I think I am back, and I think I am driving Trent's talk. So let me share my screen again. Okay, we good?
Yep.
Okay,
And
perfect.
hopefully you can hear me. And
Yep.
I'll sound like a bell when we go to the next one.
Okay.
The next slide, please, Alex.
I know it feels unfair
Yeah.
now that everybody else got to share and you didn't. Michael didn't. So.
I'll just take it as a slide against Australia, and we'll hold it against you forever. So thanks for the opportunity to speak today. And I'm from the University of Melbourne in Australia, which supposedly is summer, but it's still yet to hit the summer temperatures. So next slide, please, Alex. And I want to start, as we always do in Australia, is acknowledging the traditional owners of the country. You're welcome to read through there. I am lucky to live and work on the lands of the Dja Dja Wurrung and the Wadda Wurrung. And it's really important for us to pay respect to elders past and present and their families, and also to any Indigenous people joining us today. We know the traditional owners in Australia and elsewhere have used fire as part of their culture, and it's something that's been largely removed from how we manage lands. But there's a lot of work in Australia, particularly around fire, in terms of bringing back where possible and where safe to do so, these traditional practices. And it's something we as fire modelers need to start thinking about within our systems, about making sure we can adequately represent these processes, which we don't do very well at the moment. Next slide, please, Alex. I'll just start by saying I am fortunate enough to lead a very large group of fire researchers. It's quite a diverse group of students and staff from a diverse group of backgrounds. And I put this slide up at the start just in case I forget to acknowledge anyone as we move through. Next slide, please. So we've already heard from the speakers before a lot about fire simulation and the event simulators, and Alex's slide right at the start where she listed, I think, well, mentioned 4,000 different approaches to fire behaviour. In Australia, we have 2, maybe 3 key models that we use, but the idea is fairly simple, that we can simulate fire behaviour at a relatively fine scale. We're doing 10 to 30 metres most of the time to simulate individual events. And Michael's accuracy of about 70% is well above what we're getting from a lot of these two-dimensional fire simulators. But understanding processes, understanding the event when it occurs for operational regions is really important. And then understanding them for risk is really where, at that strategic level. One of the main things we need to make sure we get right for Australian systems, and I'm sure this applies elsewhere, is the effect of medium to long distance spotting. Many of our fires are driven by the spotting phenomena, and it's actually one of the weakest parts of most of our models. So there's a lot of work by Alex Filkoff in my group and his students in going into trying to improve that. Next slide, please. So I'm going to talk about two levels of fire modeling that we're working with and have been developing. So we have the short-term risk. So we've just heard from Robert and Melissa about some of the long-term risks, and I'll come back to our approaches there. But we have a great need to understand fire risk and how we might be using management over a short period of time. So these longer landscape fire regime models, such as presented with Landis, don't really give us that 3 to 5 year level of risk, and it's certainly overkill. It's really a sledgehammer to put in a nail for that. And so what we do in Australia, and it's been done elsewhere, and Alex and I have collaborated on a similar process, is that we run huge numbers of fires, and we're talking 10,000s to millions of fires to capture the full range of ignition locations, weather conditions, and fuel conditions, to then understand the impact on value. So we have this process that we use where we prepare the data, we run the fire simulations. We've been using Phoenix Rapid Fire and also starting to use the Spark platform. And then we combine the data from all those tens or hundreds of thousands of fires with asset loss functions and economic values to understand costs. And we use a Bayesian network approach to do that. Bayesian networks are really useful because, as previous speakers have talked about, the uncertainty in fire behavior and fire impact is quite large, and Bayesian networks allow us to capture that uncertainty and incorporate it into decision making. Next slide, please, Alex. So one of the big areas that we do a lot of work here is with energy networks, as I understand in large parts of the US and Canada, that energy fires from transmission lines are a huge issue. This is some work we're doing with one of the network providers here in Australia. And without going into the detail, but our fire path simulation pathway that I talked about before, we're able to run these across an entire network, which covers probably 80% of the state of New South Wales, which is about 20% of Australia. And we're able to then identify the areas where the largest consequences from fires are likely, ignition line fires are likely to occur. And we work very closely with the agency responsible for this area, and they actually have a multi-million dollar, it's a $100 million works program that is actually guided by this fire simulation. So the key is that we actually get this right because they're making very large investments based on these values. And this work has actually gone through a coronial inquiry and been assessed in a court of law to ensure that it's an appropriate method. Next one, please. So what we're doing is we're taking our simulations from across the landscape, and for every cell we're looking at the weather distribution here in this Bayesian network, the ignition likelihood, the nature of the fires there, and then we can come up with distributions down the bottom here. I'm not sure if you probably can't see my arrow because it's Alex's screen, down the bottom to give us the loss of different assets there. And by putting the values to it, we can come up with a cell by cell annual loss cost, but we can also then use that to come up with a region-wide cost as well. So we can identify where in the region the biggest loss for different assets occur. As Alex mentioned, we can come up with lots of pretty maps, and then we can come up with a total cost for that region and compare between regions as well. Next one, please, Alex. So we also have adapted this for the New South Wales Rural Fire Service, which is the group that's responsible for developing these risk plans. One of the interesting tricks here is they're not actually responsible for the implementation of fuel treatments. That falls to different agencies. But what we've been doing with the Rural Fire Service is we've been running this process, looking at the risk spots within 56 different bushfire management zones, which you can see in the map there with all different colours there. Thanks, Alex. And within each of those regions, they then identify a risk management strategy that they want to look at, and we're actually starting to quantify the risk in response to those values. A little bit of feedback we've been getting is that they are overwhelmed by the number of maps, as pretty as they are. And so they're actually starting to try, and we're developing methods to actually take these risk model values to give them simplified outputs so that they can actually hone in on the best map that's there that has the uncertainty as well. It's quite a challenging process because it involves people making decisions about the amount of risk they're willing to tolerate, which nobody's very good at actually putting raw numbers to. We tried very hard and we're coming up with some things, but it's still a very challenging process. Next slide, please, Alex. So what we've been working on that risk pathway, well, I've been working on it for over 15 years, and about 10 years ago, we started to think about the limitation. Well, we've been thinking about the limitations, particularly in terms of the impacts on ecological values, but also the impacts on human values, and particularly with things like smoke exposure and mental health, which are influenced by these repeated exposures. And Melissa was talking there about the repeated fires and on the environmental values. So what we did is we started to think about the limitations of what we had before, which were running thousands and thousands of fires without considering the impact of each of those fires on each other. And we started to develop a fire regime simulation tool. The reason we went for a new tool is because we actually wanted the really fine scale fire behavior details so that we could estimate the impact on human values such as buildings, etc., but also get those broad values that we could look at environmental values. So we came up with a tool called Frost, which is Fire Regime Operation Simulation Tool. And there's been a bunch of people that have been helping develop it. A couple of programmers there, Dana Beebe and Dennis Kultev, and a bunch of other researchers that have helped develop it. So what Frost does is it works at the daily time step, kicks over each day and asks, are we likely to have ignitions today? If so, if that's a yes, how many ignitions are we likely to have and where are they going to be? And then we get the hourly weather, the fuels data, and the suppression resources, and we run that through a fire event simulator. At the moment, that is Phoenix, but it's also looking at Spark as well. And then over the longer term, we can implement fuel treatments in a very similar way to that we heard from Robert there, and start to actually build up a picture of fire regimes over decades to centuries. We output a huge database. Each run can end up with hundreds of gigabytes of data, but it's the very best fire history you'll ever get, in theory, the very best modeled fire history you'll get. And then we can look at some of the risk values that are there. Next one, please, Alex. We've worked with a huge range of people, and the risk values that we are able to calculate is growing, but these are some of the base ones. We have a whole range of biodiversity metrics. We can estimate carbon values. Water supply is a big issue, of course, in many areas where the water supply sits within native vegetation. We can look at the cost of implementation of a whole range of different treatments. We've been working on the human health side. We've got lives lost, but we're also looking at exposure from both smoke for the health, but also working with Lisa Gibbs around mental health as well, and infrastructure, cultural values, and also recreational experience or aesthetic experience for social values down the bottom. This has been possible for a huge number of researchers coming in, but we've actually tied these now to very fine scale fire metrics that we can then play out over different regions. Next one, please, Alex. We can probably skip this slide. It's just to say that as it's garbage in, garbage out. So we're trying to improve the garbage that we put in it. And we're building up and publishing as we go the different components of the models to try and improve the validity of the model. But of course, there is work bringing a whole range of different things together. Next one. Actually, we can skip this one as well, Alex. Sorry, just in the interest of time. So some of the things we've been able to do with this fire behavior model, if we start on the far left, with the CSIRO current and future. So this is looking at different climates and running them through. So we took an epoch approach here. So we ran 100 years of fire with the current weather and 100 years of fire with the 2060 to 2080 weather. And we can see different patterns in where fires are occurring. And that particular area is important because it has a very tree species that's extremely sensitive to change in fire frequency. And we ran these before we had our major Black Summer fires, which impacted 18 million hectares of forest, and this area was particularly affected. The model was then able to be combined with data from Landis work that had been done in the area to identify areas where they might start reseeding this species to ensure its survival in the landscape. So we were able to identify the high risk areas of frequent fires and perhaps some of those areas where there was less risk of reburning into the future where they targeted for management. We're also able to, on the top right, the dopey looking koala bear there, which we all know and love. That's about as active as a koala bear ever gets. We're able to tie this with population viability modeling, and we're able to look at the impact of the major fire season on the population of koalas under different scenarios there within a particular area. And what we're finding is that even when we don't consider other threats to this species, which there are many, the blue line represents without the Black Summer season, and the red line represents with the Black Summer season. And the impact of that Black Summer season came out in every one of the models that we did. There's two models and two climates there, but there's likely to be a long-term impact of that fire on the populations of this species, so intervention might be needed. And then we have a couple of other examples there where we've looked at changing fire patterns, which I won't go into. Next one, please, Alex. Sorry, that's a double up. Sorry, we can skip that one. Another thing that we've been doing, and Sarah McCall-Gosden, who was a PhD and a postdoc of mine, and she was tying the fire regime modeling there with population viability models for different plant species. What we're seeing on the y-axis here is looking at the change in abundance, or the expected mean abundance of species under different scenarios compared to the current scenario now, which is the zero line. Very short, the three panels that form from those red lines basically relate to keeping most things the same, keeping a couple of things, changing the demographics and according to climate for a couple of things, or changing them for all the things that are likely to happen. And we did this in two different regions, which is the top and the bottom. But basically what Sarah was finding is, should all the demographic predictions come true for these species, and we change climate and we change fire as a result of climate, these species are going to be gone within the next 100 years, which is really quite frightening, given the relatively cautious nature of her assessments. So we were looking at able to simulate these in a spatial sense and also simulate the population changes in a spatial sense. Next slide, please. So the last one I wanted to talk about, which builds nicely on Robert and Melissa as well, is this work and these modelling systems have got great interest from our fire agencies here in Victoria, the DECA, which Environment, Energy, Conservation and Climate Action. And we took the frost model, which is the top triangle in the middle there. This is fun, isn't it, Alex? And we're combining frost with Landis. Craig Nitschke, who is also at the University of Melbourne, does a lot of work with Landis. And we've combined them to take the best of both worlds. We felt frost gave us the high resolution fire data that we could tie with human values. And then we rewrote a package to plug the fire information into Landis, and then Landis grows the vegetation, and that works backwards and forwards. As we talked about earlier, having a model and just pressing the button, as Alex was talking about, is really not the most important part. It's actually knowing how to use it, but knowing what you don't know. So we're developing an input website called Insight, which then pre-processes the data through a database, runs the model, post-processes those, and then spits that back to something called DSS Play or Display. And we're in the process of developing this to allow agency staff to actually start to use some of these quite complex models in terms of fire regimes to make policy and management decisions as they go. We've done the bottom line there quite strongly, and as you can imagine, the computing requirements for those are quite high, and we're getting a lot of feedback around insight and display at the moment. But generally, the agencies are very happy, and I think that's because we spent a lot of time working with them, developing the trust in us, but also explaining the model and how we're using it for case studies before they can start to roll it into management there. So that's a tool that's under development. It's a scary space because you're giving agencies free rein to use large, complex models, but it's been a really positive approach. And I think we're going to get to a really good situation where we've got a user group that's very, very much across these complex models that often get hidden within research groups. So I might finish there. Thanks.
And that's okay. I am not going to stop sharing, but am I muted? Can you hear me?
We're not muted.
Yes.
You can hear me. Okay. Thanks, Trent, Rob, Melissa, Michael. These were awesome. Really, really interesting, informative. Before we jump into any questions, I'm following up on the fact that we at the Global Wildfire Collective have a discussion forum. And if you put your camera up and click the little QR code here in the middle, you can post questions and we will all try to answer them and think about them together. You can learn more about the Global Wildfire Collective if you click this QR code. We also are trying to bring wildfire into international discussions and the UN conventions. So we have created a call to action for them to start explicitly thinking about wildfire. And if you are interested in our letter, you may read it and sign it by clicking on this QR code. And, simplicity does not precede complexity, but follows it. That's what we might hope with modeling. Maybe I'll actually leave these up in case somebody wants to, but Robin, do you want to lead the question and answering session?
Sure, I can see a number of the questions. I might start, Michael, with you because there were a few questions that were asked that you have already answered, but I'm not sure everybody sees the answered questions in the Q&A. So if you don't mind me picking on you first.
Go for it.
So I think one of the questions that we had was about WUI models and whether that's only modeling, or the ones that you're working on at least, are only modeling spread of the fire within the urban area, or if it's basically a path of wildland and urban.
Right. So, and this was an incredibly abbreviated 10-minute talk, but yeah. So I think one of the most important parts of the model and that differentiates what we're doing is that we are within a traditional landscape scale wildland fire model. So the wildland fire model spreads to a structure cell. The structure cell communicates, right, by the exposure from that wildland or from the exposure from an ember, whether it ignites. And then it can spread to the next structure cell by those mechanisms or back to a wildland cell. And this is really important in intermixed communities where you have, imagine, ridges and you have a valley with a lot of wildland vegetation, homes up on ridges. It's very important to catch this dynamic sort of hopscotch spread. And so that is incorporated in the model and what differentiates it a little bit. Oh, you're muted, Robin.
I have to unmute, yeah. Another question for you that came in that you've jumped in on, and actually Jonathan Hodges, who's one of our audience members, has also jumped in a little bit here, but question about basically the three-dimensional structure of winds, or how wind basically impacts the, windstorms impact the spread of fire. In particular, this question was around downslope windstorms.
Yeah, well, there are different scales to it. So wind is very important. And at the small scale, the fine scale, we don't incorporate a lot. We don't do it with wildland fire. We don't do it with WUI in terms of flows around the structures, and that's all incorporated into the submodels. But the large scale weather inputs absolutely are very important. We decouple the model because we're trying to do something fast. So when we're doing risk runs, we're going to be doing tens of thousands of different fire simulations, potentially across a very large landscape. And it's very hard to couple that with coupled weather. However, having refined, it's like using a refined WRF simulation for input weather can improve and capture things like downslope winds that you might not capture for certain areas. So, for instance, the LA fires in Southern California, you wouldn't necessarily capture all those dynamics without taking the initial predictions and then running refined models to get better inputs. There are fires where that coupling is really important between weather and fire spread, such as like some of the larger mass fires in the Sierras, or where the winds are lower, but the plume is much more dominant. That's going to dominate fire spread. So there are different regimes where you can miss things. I don't think for risk that's the approach is to go crazy computational on this, but for modeling some fires and certain behavior, some things are going to be missed in different types of models. It's about picking the right application and tools.
Thank you. Rob, we have a question for you. So this question is related to a high drought, high variance scenario. And the question is whether or not that's unrealistic over a 100-year time scale, because with such high drought, you should expect a lower plant productivity and therefore lower fuels, which could lead to a negative fuel fire feedback. Do you have any comments on that, or can you explain whether or not that would be an issue with the model predictions?
Yeah, it's a good question. It's not going to be an issue on this landscape. None of our drought trends will preclude these forests from being thickly forested. It would tip the competitive balance actually from trending towards more mesic species, maples, etc. It's going to tip the competitive balance towards oaks, which have more flammable litter. So in fact, it might be a positive fire fuel feedback loop. Yeah, in that case, where you start seeing more dominance by oaks than is currently occurring. But yeah, in no case is there going to be a substantial shift in the amount of fuels on the ground across the southern Appalachians.
Thank you for that. We have a question, that it looks like it just got answered because it jumped away from us. So Trent, I know you just typed an answer, but would you like to address Valentin's question? I'll let you summarize the question if you don't mind.
So it was a very interesting question about our model. Is there pressure to create increasingly over complex models that we don't account for overfitting, etc. And it was asked from a young modeler perspective. So I thought it was a great question. I guess my answer in two parts is that there is a base set of processes that need to be captured for any model, depending on what you're trying to represent. So the example I put in there is in Australia, in our eucalypt forest, if you didn't have a spotting component in your model of fire spread, you wouldn't be able to consider that to be accurately representing the process there. But at the same time, you don't want to overcomplicate your model, like Melissa's quote at the end, as simple as possible without being too simplistic. And there are so many models out there. So if you want to go and rewrite a new model, you've got to have a purpose for doing that new model. Or otherwise you build on existing models. And that may also be where some of the perception of massively complex models are coming from, because we're building on what's already there to try and improve them. And it is challenging, and it takes time. I think that's the key thing, is a lot of these things don't just appear overnight. They can take 10 years to develop or more. And in doing so, you're capturing all those little criticisms you get along the way. So a new modeler shouldn't be trying to jump to the end line. They should be thinking about their research pathway.
Excellent. Rob, you have your hand up as well.
Yeah, I wanted to jump in on that question. As Trent said, it is a real challenge, and there is a tendency that models grow more and more complex. But I think there's also opportunities as we get better data to simplify our models. It doesn't need to be this continual progression towards more and more parameters. Sometimes you actually just need better data. And that's, so we developed the social climate fire model about, oh my gosh, Melissa might have to remind me, was that 2015? No, 2017, let's say.
Yep.
And part of it was we were trapped kind of these bottom-up fuel models run with these road terminal equations, which just have dozens of parameters, which are not empirically measurable. It became a trap for us because we're doing these longer decadal simulations. So we said, well, let's just back up and let's just use the satellite data from the last 30 years to build a model, which is radically simpler. But it's only possible because that data existed. And, these big data like MTBS came online and all this, data became available that we could start looking at fire spread patterns over time. So yeah, things often get complex until you reach a point where it sort of breaks and then you kind of reset if there's good data.
Melissa, we haven't heard from you yet, and you've got your hand up.
Oh yeah, I was just going to say part of the question was about educating users, and I think Oregon is a good example of where that's been really challenging. As many of you know, in Oregon, just a few years ago, we released a new wildfire risk map, and there was a huge blow up associated with that, with individuals looking at their fire risk assessment on their parcel and disagreeing with the assessment. There were death threats made to the developers of the wildfire risk map and all the staff. So I think that that's also a real challenge, is communicating the results of these wildfire risk assessments and projections with the public. I think can be really challenging, and that map was recalled and a new one was released and was much better received. So I think there's been a lot of lessons learned, but a lot more that we still have to think really carefully about how we're interacting with users in terms of our wildfire modeling.
Excellent, thank you. Michael.
Yeah, I just want to add on Valentine's earlier question, which is that Trent was going on. Something that also comes up a lot here in California is that it's not just the academic modelers. There's been a push within academia to do more open modeling, meaning codes and data is available on GitHub or in other resources so that people can actually run, compare, and fact check, and that things are published openly. But within the industry, it's not. And even within academia, most codes are not, right? So there's a push to sort of move in that direction. But I think that also, when we talk about, trust, because if you notice, so many models are incredibly tunable. There are very little adjustments that can drastically change them. And then when you have black boxes, there's even more question about the inputs and about how parameters within the model and how they're all tuned. So just because the physical model doesn't mean you know how something was actually run. So I think there's some really good points about enhancing the data that we have in the future. But I think we really need to think about making sure that the process is open and also that we develop more methods, especially where some of the modeling has big implications in California for how we do, power line shutoffs or how we look at mitigation dollars. These are billion-dollar questions, and we don't validate, verify, or look at the sensitivity of the models. And this can have big implications if it's not really spelled out. And it's a hard thing to communicate, but I think that's a path that we should go as well as an academic field, and trying to make sure that we come up with methods to add more trust, or at least add the error analysis to the model so we know the true uncertainty.
Excellent. We have one more question coming directly from the audience. So, Sashi, I'm going to, I guess, allow you to talk. I haven't done this before, so if it doesn't work, we'll find out. I'm asking you to unmute so that you can then speak. Sashi?
Okay. Can you hear me?
Yes, we can.
Okay. Well, thank you. So I am kind of got two hats on. I'm with PG&E. I'm a Chief of Wildfire and Climate Resiliency, but I'm also on the board of Fire Safe Sonoma. And that's partly what I'm kind of asking for here. Michael, I really appreciate what you're saying about wanting to have transparency of the models and have people be able to connect that to actions. So I wanted to see what people thought about how you can communicate how these models should be translated into actions. Because I think what people want to know is, well, okay, so what does that mean for my property, or what does that mean for my neighborhood, or how can we highlight the most risky areas, and how can we make sure we only really work on the things that are the most risky. So I know that I really appreciated Alexandra's comment at the beginning about the different timescales. Is there a way that you can communicate about the use of these models that just keeps kind of going back to those different timescales and how you can make these things actionable for people?
I think one thing that helps is when a modeler produces results to specifically say, here are what these results can be used for. Here are the guidelines. Can you not hear me? I see Robin.
Oh, I can hear you. I don't
No,
know if
the
everybody
I
issue
hear you
is
loud and clear.
You're good.
I'm not quite sure if you can hear me.
We can hear you. I was having an
Okay. Okay. Anyway, I think a lot of it just has to do with communication and saying, here are the limitations of our modeling approach. This is how you can use it to make decisions. These are the kinds of decisions that you can make. Here is how much variation there is in the results. Here are the ranges of results that you could expect. And here's the ranking of the results relative to those ranges. And, to consistently remind people that models aren't necessarily meant to predict a certain event at a certain place at a certain time. They're help you to rank things and predict things and say, we're assuming that over this period of time, these results can be used this way. So that's one comment I have, and I see Trent has your have your hand up.
Thanks, Alex. Yeah, we have a real challenge in terms of what we release. There's one argument of releasing every bit of information for everyone, but we also know people will misuse that information, and that's not just individuals. There might be other groups which may profit from using that information for other reasons. So I think absolutely being very careful, but getting down to the property level, I feel is really quite dangerous. So a lot of what we do is actually, I'm trying to think, but we put a bit of noise around, not noise, but we average the data over bigger areas so that it can't be attributed to individual properties or even individual sets of houses, to ensure that the risk value patterns, like Alex is saying, is seen over landscapes and within regions, but really not at the fine scale where we know the models are most uncertain, and that interface fire spread, like Michael was talking about, very complex process and really dependent on what happens on the day and some very fine scale features. So I think that while the desire is there to put out as much information as possible, we know that there are always people that will manipulate that. So we've got to be very careful.
Okay, Michael, I'm going to give you the last word because we've run over time. So I'll give you the last word. If we haven't gotten to your question today, I would highly recommend that people scan the QR code in the center of your screen right now. Most of the folks that are on this call are already in this discussion forum. If you're not, I'm going to hunt you down and put you in it. But we can continue this discussion in the Q&A there. So go ahead, Michael.
I just add there was a New York Times article. I know Zillow, which is the big home, you know, app that we use to look for real estate in the US. There's others, but it's the biggest. Uh, Dropped their use of fire risk and other disaster risk scores because of this very problem. And realtors, particularly in California, were complaining about individual structure assessments. That was from First Street. So, it's this complicated thing because you really want to give people individualized information that they can act on. And at the same time, you know that they don't actually have enough fine scale data to do it, and people are arguing about it. And even in the larger scale mapping in California that they use to enforce codes and with FRAP uses for the fire hazard severity zones, lots of pushback and years even within officials pushback before they decide on regions. So it is complicated, and I think was mentioned here, right, that there's a social context that often isn't thought about in the modeling that needs to be included when this is all put together.
Excellent. Well, thank you very much, Alexander. Anything you wanted to add before we wrap up for the day?
No, other than thank you so much again. And this webinar will be posted on YouTube. So anyone who wants to go revisit anyone's slides can go there. We will be sending out a link to everyone who registered. And if you have suggestions for future webinars because you're so interested in modeling, let us know and we'll see what we can do.
Absolutely. Thank you again, everyone.